So what I want to talk today is about studying of some limits that we will see how logically it would be to call a soft limit in theories which are defined in asymptotically AdS spaces. Okay, that's what the title is about. So let me go ahead with some known facts. Okay, so some known facts are following. So this is regarding soft theorems. Now pertaining to, just a second. So soft theorems pertaining to amplitudes in asymptotically flat spacetimes. So this is something that we all of us know by now very, very well. So these theorems basically relate scattering amplitude with soft particles, let us call them to be photon or graviton, either of them, or Young-Mills fields, to amplitudes without any soft particle. Okay, that's what is the prime point of soft theorem. So here I have tried to just very schematically write it for you that if we have a scattering amplitude of n+1 particle where one of the particles is going soft, so this q is the momentum of the soft particle and epsilon is the polarization of the particle. Depending on photon and graviton, it will differ. We know that this n+1 point amplitude can actually be expressed in terms of an n point amplitude that entirely depends on the hard particles, and then an universal factor which is called the soft factor. Okay, so these are work of course by Weinberg, and then lot of interest in recent past by Lau, Cachazo, Strominger, and Sen and Latha. Okay. So this expansion, the expansion that we have written here, is valid when the photon or the graviton frequency, the omega, is very small compared to the energy of the other particles. So compared to the other momenta, PS, QA is small. And the soft factors, as we know, can be expanded in leading order or subleading order, or even in subleading order in terms of frequency expansions. These are universals in flat space-time. Particularly, it's universal up to leading order in frequency for photons and to subleading order for graviton. And these are also invariant. This is a very important point, that these are also invariant under gauge and general coordinate transformations, respectively for photons and for gravitons. So their derivation, the derivation of this theorem, actually follows from gauge and diffeomorphism invariance of the fields in asymptotically flat spacetime. So this is what is the main reason for having such a theorem in these theories, because we have these local symmetries and associated massless field for whom we can always take the soft limit, and that gives us this nice property that we have written here. Okay, so this is a very, very well-known fact. Now, based on these facts comes the goal of our program. Okay? So the first point to note is that gauge invariance or diffeomorphism invariance, I'm calling both of them together as gauge invariance, this remains intact in asymptotically non-flat theories as well, particularly if we are interested in AdS or DS theories. So thus, since the gauge invariance is the prime reason for having soft theorems, so we can expect a version of soft theorem to exist on space-time such as AdS and DS, asymptotically AdS and DS as well. This is a point to think about. Second point is, so we know that AdS CFT, as we believe in it, it demands that every physical aspects of the field theory must have a counterpart in the dual gravity. Okay, thus soft theorems, which are like which are statements of the field theory, must also have a
Hello? Can't hear Nabamita.
Oh, she's not audible.
Yeah, I cannot hear it either.
Does she know that she is not audible?
I'll give her a call.
Yeah, I think.
Okay, maybe her phone is on silent for the talk. She is not answering. I'll message her. Arpita or Arnab, do you have her office number? I
called her, so maybe she will be available. Yeah.
Okay, thanks.
Yeah.
Hello, can you hear me?
Yes, now you are audible.
Okay, just
Yeah, so we couldn't hear you for last few minutes.
Yeah, I understand that. So I just saw that my slides are not changing. So just give me a minute. I have to rejoin. Okay.
Okay, sure.
Can you hear me now? Can you hear me?
Yes, you're audible now. Fine.
Thanks. Just let me share again. Okay. Good. Okay. Fine. So I think Tabassum, if by chance anything goes wrong, just call me in my office. Okay. Thanks, Tabassum. Okay. Good. So I'm audible, right?
Yes.
Yes, you are audible. Yeah.
Okay, so the prime issues, okay, so I was basically telling you that what are the goals of my programs. So the goal is to basically find a suitable physical observable in a theory, which is asymptotically AdS, and then probably study their universal behavior, if any, in a quote-unquote soft limit. So,
Nabamita, can you move the logo of the Zoom up somewhere because it's blocking?
Done?
Yeah.
Okay.
Good. Thanks.
Thanks. Okay. So the prime, okay, so is the goal clear? Okay. And please feel free to stop me at any point if you want. Okay. So what are the prime issues to the goal? One issue is following that on asymptotically AdS spacetimes, we know that there exists no asymptotic null boundary. Okay, so that's a problem. And hence, the usual flat space S matrices cannot be defined. I mean, there are, of course, many references, but the one that I personally like is this one by Banerjee. And then this is one prime issue. So the way we think about soft theorems are characteristics of scattering amplitudes, and that aspect cannot be trivially taken forward to theories in AdS spacetimes. And the second point is following that due to the presence of cosmological constant, Now there exists an inherent length scale, and that prevents us to take the strict soft limit, the zero frequency limits for particles, for any particles, as we do for our usual soft theorems. So these are two prime issues that we need to think about when we would like to go for our goal. Okay, and hence the question remains that how do we proceed? So let's see. Okay. So before I proceed, I'll like to remind you of some more facts. And that is about classical soft theorems. Okay. These are some other set of theorems now pertaining to fields in classical scattering processes. Okay. These are widely studied by Latha and Sen, and then nice proof is given by Sahu Sen and Arnab Priyashaha. So what? Hello? Hello?
We can hear you, Nabamita.
Okay. Yeah, I mean, I just thought maybe I got disconnected. Okay, good. So the universal contribution in soft factors on asymptotically flat spacetimes can also be found by using the radiations arising from classical scattering processes in the vanishing frequency limit. Okay, this is what is their result. This is what is the result of Latha and Sen. For this, of course, the external momenta must be considered much large compared to the Planck mass. And if, just to take an example, the classical soft photon theorems reads like this. Okay? So if we look at the electromagnetic radiation mu, where epsilon here is the corresponding polarizations. So these radiations, if you expand it in the zero in its frequency, then the zero frequency limit of the radiation knows about the factor that arises in the sound. Okay, and one can nicely prove it also. So this is an alternate way to look at.
Sorry to interrupt, Nabamita. External momenta have to be larger than M Planck, is it?
Yes.
I see. For obtaining the soft theorems?
For obtaining the classical limit of it.
Oh,
so
I
here,
see.
yeah.
Okay.
So here by yeah.
Thank you.
So then what one needs to do is following. One needs to take a Fourier transforms of the radiative field in the long distance, and this is proportional to the classical limit of the soft factor. So what do I mean by classical limit of the soft factor? The soft factor, as you know, it depends on the momenta and angular momenta, depending on which one you are looking at. And in the classical limit, all these operators of the quantum theory needs to be replaced by their classical counterpart. Okay, so when one does that, that's exactly the factor that one can read off from the frequency expansion of the radiative field. So this.
Sorry to keep interrupting, but just to make sure, you can't obtain the classical theorems with momenta much smaller than the Planck mass, but just very big amplitudes, you know, the typical classical limit in QED where you have coherent states and so on, but the frequencies are small or can take any value. That's not good.
So here what is, okay. So for the classical soft theorems are following. So I need to compute the radiation, okay, and then I need to take this limit. I need to look at the how would I say? Yeah, I need to look at the beam that is coming out, and there I need to take this consideration that every other hard particle must have much larger energy compared to the soft particle.
Right, but so, could that just be parametrically as a ratio, or does the Planck scale come? I mean, if I was just doing QED, it should be possible to do it just in terms of parametric ratio.
I agree. Yes, I agree. I agree with you. So just for the class, I mean, yeah, okay. Let me reiterate. So if my intention is to just understand the classical scattering, then this is not required. Okay. But what this process actually tells us is even the right hand side is a quantum effect, right? The soft factor is a quantum effect, and one can also get its corrections order by order. The classical radiation seems to know all about it, of course, in the classical. And here by classical limit, I only mean that the corresponding operators needs to be replaced by their classical values. So if you want that aspect also to be included, then this is required. Otherwise, just for studying classical radiation, no, it's not required. All I need to make sure is that the hard particles have much larger energies compared to the soft one, and that's what the detector is going to measure.
Okay, thank you.
Thank you, Sandeep. Okay, so but one aspect that really goes into this computation is following that we need to parameterize the initial and final asymptotic trajectories of the probe particle. Again, I must refrain myself. It's not important that we have to do this in probe limit only. Ashok and Sahu and Sen, they have done it even without considering the probe limit, but probe limit is just an easier way to get to the results. So I'll mostly be concentrating on that. And when we do that, we need to know like the scatterers are coming, there is an interaction happening, and then it's again going out. So we need to know the initial and final trajectories of the probe particle. That one has to parameterize properly and then do the calculation. Okay, so say for example in 4 dimension, we know that a non-relativistic particle in the radially outward trajectory can be expressed. The equation of motion can be expressed by this equation, where right hand side is just the inverse square force, and then the trajectory can actually be parameterized by an equation like this. Okay, and so here PIs are the momenta, the classical momenta. We can also write down the angular momenta for these particles, and that just turns out to be this quantity. And then we can write down. So what I mean, you find the classical. You find the profile, the mu, and then study its Fourier transform it to the momentum space, and then study it in the low frequency limit. What you get if you replace tau by omega inverse, you exactly can read out SEM from that, where SEM now will have 2 parts. One is the one I have denoted as the leading soft part, and even the subleading soft part, which in 4 dimension goes with log omega. So both these terms can actually be obtained just by studying the radiation in the Fourier space in the low frequency. Okay, these are known. Sorry.
I have a question. How do you get this x mu dependence on the tau? I mean, is it a solution of the equation of motion above?
Yes, I have just written it in the covariant motion. Yes.
And where is k here?
Where is what here?
K. I mean, k should appear in the solution, right?
Okay, no, it's the momentum. Acha, okay. I have done it for in generic. I mean, there is CI mu's and BI mu's. These are all our coefficients, right? That one. Yeah. Okay, so that one. Yeah. Okay. Fine. Can I go ahead?
Yeah. So, sorry, Nabamita. And then when you write it in terms of the moment, in terms of non-analyticity in omega, I guess. That's the lowest expression you have, is it?
No. Okay, so the first term, so this one goes as 1 over omega. Okay, but the next term does not go as omega to the 0. This one goes with log omega.
Log omega, right?
Yeah.
Right.
Okay. But with this pinch of salt, that's what I have to do. This term actually goes with log tau inverse. If I replace tau by omega inverse, then I get it in the usual soft notion. Okay. So that's what is the prescription of classical soft. But at the end of the day, what is nice is following that one can, by studying, just by studying the radiation profile in the Fourier space and then studying its behavior in the frequency expansion, small frequency expansion, can read off the soft factors from it. Okay, that's the result, and this is what these soft factors, which is related to the quantum soft factor in its classical limit. This statement is known as classical soft theorem. Okay, good. So these are known facts, and then it gives us a hope that we can probably approach our goal, which is to find some kind of an object and study its soft limit from a classical perspective. Okay? So that's what I'm going to do, a classical approach to the goal. So the first approach is to try to understand or to find this classical version of soft theorems in asymptotically AdS spaces. because this question is much more well defined. So let me see what scattering process in this ADS spaces with a small cosmological constant or with a large radius. Okay, so we will think of it that we have an asymptotically ADS space, but this space is really from my flat space because of a presence of a very, very small cosmological constant. So that is what we are going to do. And in this space, we will study a classical scattering process in the probe approximation. So at this point, I mean, when we first started this program, taking this large AdS radius limit or the small cosmological constant limit was really a tool for us for technical simplifications, because I could see that is where I can perform the calculation. But later, as I will present in this talk, we will see that this limit, the large AdS radius limit, turns out to be an essential physical input for the computation. Okay, I'll explain it as I go.
So, sorry, Nabamita, I should wait, but may I ask a question about this limit, if you don't mind?
Please, please ask.
Okay, no, thanks. You know, what's slightly worrying me, I'm sure you'll address it, is that the limit R going to infinity, that is where you go asymptotically far away, and L going to infinity don't commute with each other. Namely, you know, if you keep L finite and go very far away, you will see AdS space, which is different from flat space. Whereas, you know, if you keep, if you take it the other way around, then you will see flat space with corrections, perhaps. So is there an issue of how you take the two limits, the asymptotic?
Yeah. Yes.
Okay.
So I will basically, since you already gave me the two scenarios, I will tell you that I will actually end up in the flat space patch. Okay. The way, and I'll explain to you why it is so. Okay. So again, like thank you, Sandeep, for asking the question. So when we were starting this program, see, when my intention is to just study a classical scattering process in the probe limit in this space, there was no reason why I should be considering small cosmological constant or equivalently the large AdS. Okay? But we did it just for technical simplifications. But later, I mean, slowly we will understand that where it is taking us to, how to make sense of the results that we are getting. And that will eventually take me to the flat patch that we just talked about. Okay. So just to tell you, just to give you the flavor of our results. So what it is going to do for us is it is going to give us the leading 1/L² collections to the known flat space-time soft factor results, because that's what we are actually doing. In the classical scattering process, all I have done is I have thought of AdS, I have thought of adding a small AdS potential around my flat space, and I'm just studying the effect of it perturbatively around my flat space. That is what I am going to do. Okay. So the probe scattering in AdS space-time, some technical points. Okay. So as I said, this is for making sense of the classical result. So we should be first considering scattering of a probe particle of mass small m and charge small q. Okay, so that is what is the probe particle is denoted by, and we are studying it in an AdS Dyson-Nordstrom black hole background with a very small cosmological constant. So our lambda is going to be small. That means we are always going to work in larger limit, and the mass of the black hole and the charge of the black hole is much larger than the mass and charge of the probe particle. So this in a way will make sure that the impact factor of this scattering is large. Okay? So the gravitational action is just this, like r minus 2 lambda and the usual f squared term. One can write down the equation of motion for the metric tensor as well as for the beach. So this is simple, and the background for this space time, now we can write it down. So again, for studying radiation, a coordinate system that's very useful is isotopic coordinates. So we are going to do our calculation in isotopic coordinate systems where the metric is given in this form. I mean, we can write down the metric in this form in this coordinate system. And then of course, we are working in two limits. First limit is this, where Q and M, in general, Q is less than M. Of course, in the extremal limit, they can be equal or related by a factor of G. And that is much less than my R. Okay, where the point where I am going to measure the radiation. So R is nothing but mod of it. Okay, and then for simplicity, this is what Sandeep you were asking. So we are further considering that this R, I mean, where my measurement is being done is much less than the AdS. Okay, so I can think of myself to be basically in a lab where the size of the lab is much less than the size of the AdS. And in that lab, I am measuring the effect of my radiation. That's what I do.
I understand. Thank you.
So this is my metric, as I said, and the gauge field profile can also be found. That's the gauge field. So yeah, where phi is nothing but this quantity, and we are always going to work in the order that we. So one very important point here is this. So whatever the question.
No, please, Nabamita, please go on.
Okay. So yeah. So whatever we are doing is following that. Although my goal was to study classical radiation in asymptotically AdS spaces, but what I really am doing is I'm studying the radiation in a space-time that describes AdS only up to 1/L². Okay, so I mean, that is what we are doing. But physically, this is same as studying a system with a very small cosmological constant. Okay. Now, of course, yes.
So what is the exact value of G0 and Gij? I mean, I suppose you have written it in the limit R is much less than L, but what is the exact value?
Well, you have to keep on other terms as well. So first of all, I have written it in these coordinates, in the isotopic coordinate. Okay. So you can first of all, as you can see, right, it will have other, so it's just a AdS Reissner-Nordström black.
True. And that's what I'm asking. What is the G0 for the AdS Reissner-Nordström metric?
So it depends on in which coordinate system you are looking at, right? So depending on in whatever coordinate system you want to look at it, you will have more terms. So in this, the coordinate system that I am working on, whatever I have written is the metric up to 1/L². If you want to keep other terms, then you have to keep other terms.
Okay, go ahead.
Okay, thank you. Okay, so of course, from the rest of the calculation, we are going to treat phi as small, because I have always considered that we are studying the scattering in the probe limit. So that means that phi must be small. And also on top of that, we are considering this particular limit where the position of measurement R is much less than the size of the AdS. Okay, so that's my background. And in this system, I am going to part up with a particle of mass M and charge Q tilde, and that's what should be the action of the particle. I mean, the trajectory would be governed by this action. Okay. Now, all that now I need to do is I need to think of it as a perturbation to my system caused by the stress tensor. This to be the stress tensor and this to be the charge current, and then study the effect of the perturbation and find the perturbation. So once I can do that, I know my radiation profile for my metric as well as for my gauge field. And then I have to study this radiation in the soft limit to get the classical soft factors out of it. So that is what I'm going to do. Okay? Of course, the calculations are technically involved, but that is, that's not the point of the analysis. Okay. So
just to make sure I'm understanding, so you've got a particle moving according to some geodesic, and then what? It falls into the black hole? Or
yes. So it comes. Yeah. So there is an impact parameter of my theory, and the impact parameter is very large. I mean, okay. In principle, yes, it will come and fall into the black hole, but the system that we are studying is a system with large impact parameter. So it can only come as close as possible by that. And then it will, okay.
This is almost like Eichenol kind of stuff, like very far away. Okay.
Right.
And then because there's some small acceleration, there'll be some small amount of radiation, and that will be the Lee-Narvikar formula for J and gravitational unlock for T.
Right. Absolutely.
Okay. Thank you.
Okay. Yeah. So only thing is that right now in the potential, we also have the effect of this AdS. Okay, up to, by AdS, AdS up to 1/L². That I need to keep and find the definition. So that is exactly what would be done. I mean, we have done. So this is something a long back work by Peter. He did it for Schwarzschild spacetime. We just studied it a little bit away from his analysis. So, I mean, yeah, as Shiraj said, all the thing that I basically have to do is you need to write the part of Maxwell equation, which is smaller. That's why I have given. And of course, the metric equation as well, that would be long, but that's fine. We can write it down, and then the steps to solve these equations are following. First, we will solve the equation to the 0th order by finding the Green's functions of the flat spacetime de-Alembert operator, and then the next order terms will come in the part derivative expansion to the order of m, where m is the mass of the black hole, and to the order of 1 over L square, where this 1 over L square is coming because now I am in AdS. So that potential is also going to affect my calculation. So of course, the flat space Green's function now will also have corrections because proportional to, I mean, I have just written it as 2 more Green's functions if added up to the full one. One is due to the mass of the black hole, and the another one is due to the small AdS potential. Okay, these are like the tail terms to the flat space scalar Green's function. And then putting them back and doing some computations like the linear widget potential kind of a computation, finding profile in that kind of a potential. One can write, I mean, we can find the gravitational radiation as well as the electromagnetic radiation. Okay? So that's it. We find it. And then, okay, sorry. And then comes the point, okay? After we have found these two...
Can I ask you, but it's probably a very stupid question. In the absence of a black hole for a moment,
yes,
then this particle would be going on a geodesic in pure AdS, and in all geodesics and pure AdS are the same. So this is sort of like the particle at rest. So that causes no radiation, right? Is that just
yes?
Okay. So the black hole is completely essential. So you will.
Yeah.
Okay.
Yeah. Okay, it is, and then we will see some. I mean, let me get to the result, and I'll state some. Okay. Okay. So then, what is my next step to write down the classical soft theorem? Is to study the soft limit of these radiations. But there comes our first issue, right? Because we don't know how to define. I mean, by the time, the usual definition of soft limit is not applicable in this case because we are in AdS space, and hence the frequency cannot strictly go to 0. Okay. So that was our issue, and that is showing up at this step of the computation. Okay. So how do I encounter it? So here comes a physical input, and the input is following that as the effect of the AdS potential reduces, we actually approach the asymptotically flat space, right? I mean, even just from our beginning point, if there is no cosmological constant, it's just a flat space-time calculation. So we can think that when the AdS radius is becoming larger and larger, in that limit, the frequency of this radiation should also go to smaller and smaller. Okay, as L goes to infinity, the frequency should approach to 0. So that's the physical input at this point. And taking this input, let me write down the so-called soft limit, quote unquote soft limit for my asymptotically AdS spacetime theory. Okay, so that's what I'm defining. In yes.
Sorry, are you putting boundary conditions at R?
I'll comment on it just in the next line. Okay.
Okay.
Yeah. Good. So just to tell you, yes, it should be a AdS boundary condition. Okay. But I'll take
AdS R.
Yes. In my box. Yes.
Your box. So you're putting like Dirichlet type boundary conditions on your box.
Yes.
Okay.
Right. Yeah. Okay. So now just to redefine, I mean, just to define the limit mathematically, what we are doing is we are taking omega goes to 0 and L goes to infinity, keeping omega L fixed, and that I'm denoting by gamma, but I'll take this fixed quantity to be large. Okay, so that means, yeah, as L is going faster to infinity than omega is going to 0. That's my limit. I am going to study this radiation in this limit and see what I get. Okay. Now, of course, as I said, that for doing this analysis, I need to parameterize my trajectories, and that is what I'm doing here. Now, here, as Shiraj was asking, that now it's not just the inverse square force, right? I also have an additional potential because of the presence of AdS. So, of course, my trajectory will change. But the change in the trajectory that once I put the boundary condition that I will get would be something like this. I mean, not something like this, it's exactly like this. One can do the calculation and get the correction to the trajectory. But what we will see is, to our order of computation, this will not affect the radiation. The radiation, the A mu or the G mu nu that we are going to compute from here to the order of 1 over L square will not get a correction from these two terms, because this will affect me to the higher order. So to 1 over L square order, we can still, and within the box where we are working, where we are performing the classical radiation, the classical scattering, in that box, I can still, the effective part of the trajectory is exactly going to be the same as to that of the flat space. And that is
a question.
Yes.
So where is the effect of the phi here? I mean, you had a phi in the effective.
So the phi is related to, just let me change my pen. I hope I can do that. Phi is, you mean this phi, right? Can you see? It's visible.
Yeah.
It's M by R, right? That was the profile. So I'll put it back in my calculation and do it. And I'll work in the limit as I showed you. Just let me.
Okay.
Just a minute. I'm sorry. Yeah, we are always going to work in this limit. That's the large impact. Okay. So we will have an effect. In particular, let me just give you more. Yeah. So that will give me this tail part of the grace function. Okay. Fine. Okay. Yeah. So this is what we finally get as the classical soft factor.
Now, within your box, T is always less than R, roughly, right?
So R is the point where my detector is. Yes, right. It should be. Yeah, it is the asymptotic point.
Right, and therefore the full time of trajectory is set by order R.
Yes.
T is always less than R, so the parameter that justifies your neglect is basically R squared by H. Is that right?
Yes. Yes. Okay. No. So in the next step, okay, thank you, Shita. So now I got it. Okay, by I got it means I studied the classical radiation in this particular limit, and then I see that in that limit one can find this factor that looks like a soft factor, and it looks more close to a soft factor when you rewrite them in the covariant notation. I have just given here how should I parameterize the momenta and how should I parameterize the angular momenta. Is there a question? Okay, no, sorry. So when you put it in your expression, then you get that these are the corrections to the soft factors, classical soft factor, because of the presence of the cosmological constant. Okay, this is the leading order term, which goes as 1 over omega, and this is the subleading order term, which goes as log omega, and both of them are actually to the order, it is to the order gamma square, which is gamma is nothing but omega, which is a large but fixed parameter for me. That's what it is, and one can show that these expressions are also on shell gauge invariant and diffuse. So that's good. So that is what we have obtained.
So
yes.
I would suppose that there would, by this leading and subleading, I would suppose that there would be a term corresponding to the flat space.
So this is the correction to that.
Correction.
Yeah, this L is denoting that I definitely have a L0 term, which is coming from the classical part, and then this extra part is now coming to my soft. Okay.
Sorry, Nabamita, what is little l, that parameter in the denominator?
This is the AdS radius.
AdS radius. Okay. So these are the leading corrections in 1 over the radius square. Huh?
Right.
Okay, got it. Thank you.
Good.
I'm sorry, Nabamita. So, yeah, could you go back to the previous slide if you don't?
Sure.
Yeah. So what is the momentum of the photon here? Is that
momentum of the photon is q, small q.
And that is the thing that is becoming 0.
Right.
That's the thing that's becoming 0. I see.
Yes.
And both of them seem to have the same denominator to me, this leading and subleading. So I was getting confused about why one was leading and the other was subleading. Sorry for the stupidity.
No. Okay. That is because the other term, this term will also come with a log of omega. I mean, okay.
Yeah.
This time, okay. So I'll just give me a minute.
Okay, fine.
Yeah. This is how it is. Okay. One comes with 1 over.
Oh, I see. One log of omega there. I see. And what is omega? Omega is the energy of Q.
Yeah, energy. Exactly.
Okay, thank you. Thank you. Now I understand. Thank you.
Okay, good. So this is what we can get by doing our classical analysis. Only good point here is that maybe we have been able to identify the quote unquote soft limit. Okay. Now let's see if we can approach this problem now like full-fledgedly. Like by that I mean more in the line of flat space soft theorem. Okay. So quantum approach to our goal. Yes. Question.
Answer on the previous slide, universal in some sense? Or
Can you repeat your question?
the soft theorem that you got, is it universal?
It is universal. See, because it does not depend on the mass or the charge of the. It is universal. Yeah. Well, thank you, Abhijit. Yeah.
Also, it's only using the Coulomb, right? It is a unit.
Yes. In fact, that's a very important point. That we are. I mean, it seems to us that we were reaching closer to the goal because we have been able to identify some universal factor in this process. Okay. Good. Can I?
Sorry, just to repeat Abhijit's question. In the black hole metric, there is a part which has, is linear in your phi, and then there are parts that are quadratic and so on.
Right.
So the things that are quadratic and so on would depend on the structure of the black hole, whether it's a star or a black hole.
Right.
But the part that is linear and phi would be universal, right? Just determined by charge and mass. And your answer was only depending on the linear part, perhaps.
Right.
Okay, thank you.
Okay.
And by universal, what exactly do you mean? Universal?
Is it different from a charged star? If it's a star with some charge and a star Q and mass m, or a black hole with that same thing, is it the same?
Yeah, exactly. That's what I mean. Exactly.
So what is meant by universal?
So it doesn't.
Sorry.
So it does not matter what is really going into this the constructions of the. I mean, in other words, it will mean that it does not really depend on the details of the theory where this black hole is created. Okay.
You mean the other particles that are scattering can be of any spin? Is that what you mean?
No.
The other particles that are scattering in the amplitude, they can be of any spin and any.
I mean, exactly. I don't really. This result does not really depend on the details of the theory in every aspect that you can think of. Okay. As soon as your theory admits a soft particle to all quantum level, in particular, our analysis has just been the classical limit of it. Then the classical radiation sees this factor. Okay, good. So
sorry,
then,
Nabamita, you have to go on, but very quickly.
No, it's okay.
Okay. Can I ask you also just in terms of a non-relativistic limit? That is, can I just think of it like this? You basically have the gravitational Coulomb potential.
Right.
Okay, some correction due to the curvature of AdS. And then you have a non-relativistic particle which goes slowly and traverses that and gives up some. Can I think like this?
That's this result.
Okay.
Okay, I have just written the same thing in a covariant form. Nothing.
Sure. Okay. No, nice. Thank you.
Nabamita, another way to state this universality, would it be correct to say that if you have multiple black holes or more complicated processes, as long as you look at what is happening to a single photon at low energies, this would be factor. Is this
Absolutely
correct?
Yes, that is correct. Yes.
If you have multiple black holes,
I can have. I mean, I do not really care about what that aim is. What exactly goes into the construction of that file.
okay.
I think you're very far away from whatever is gravitating, right? You just see the leading one.
Yeah. So right, Sandeep, and that is what at some point I thought, is it any point of doing this analysis? But let me just get to that point.
No, please. Yeah.
Yeah. Okay. So now the quantum approach to our goal. Okay. So basically, what we would
Oh my God.
I mean, some observable in the full theory, asymptotically AdS theory, that hopefully should show some universal behavior in the double scaling, I mean, in the soft limit that we have just done. And then the next step would be that I should also be able to understand how to take the classical limit of that result, and hopefully we get back this, whatever we had. Okay, that is what would be the next step to take. I mean, that is what I thought of take. I thought that one should be doing. Okay, now to do this, let us understand our limit a little bit more. Okay, what is this limit that we are, I mean, what this limit is really doing to us? To understand that, it's better to look at AdS in global space. Okay? If I look at AdS in global space-time, the AdS4, I have only written it here for AdS4, the metric looks like this. Okay? The rho is like the radial coordinate, and rho equal to pi by 2 is the boundary. Tau is varying, is like the global time. It goes from -pi to pi, and d omega is the coordinates on the 2. Now, if I take a large L limit of this space-time, of this metric, and redefine my time as t via this relation, and r, the position, as this related to, I mean, I'm basically scaling both of it with L, then the metric that one gets is following. Okay, and this metric is, it is basically pushing me to the center. I'm zooming closer and closer to the center of the AdS, and there I basically see that there is a flat density. So the limit, what it has done for me, very nicely, clearly visible in the global coordinate, is that in the larger limit, it has basically pushed me from this entire bulk of AdS to its center, where there is a flat space-time. And all my computations that I have done is within this region. Okay, there, I mean, in fact, within this part. So my scattering has happened somewhere here, and I'm measuring its effect in this boundary. That is what we have done. Okay, so the 1/L² correction that I got can be thought of as a perturbation to the flat space-time result. I mean, it is actually just the correction to the flat space-time result, and also as it is realized across the null infinity of this flat patch that is at the center of the AdS space-time, and it only sees the effect of the AdS potential when the potential is very, very small. So,
sorry, is the understanding that locally everything is flat? I mean, the space is space is flat. Is that
locally? Yeah, it is not. I mean, locally, I think all space-times can be thought of like that. But what I'm trying to say is the large L limit is doing this. Okay, so my space-time is it is a AdS space-time only, but I am looking at AdS space-time only in the large L limit. What it is doing in that limit is it is pushing me in the center of the AdS, and there the space-time is in that entire region, the space-time is just a flat space-time.
But
okay, and what we have done is we are studying the effect of this AdS potential, very, very small AdS potential around this flat space. That's what.
But what I'm confused by the fact that the large L limit is applicable all over the space-time, right? I mean, all over. I mean, it's not that the large L limit is applicable at one point in the space-time and not applicable in
not at all. So this is my space-time. Okay, at all value of tau ranging from -pi to pi, for all rho ranging from 0 to pi by 2, and then for the sphere coordinates z and z bar. This is the global metric everywhere in this regime of coordinates. This, if you take the limit, L goes to infinity, and you rescale your coordinates t and r as following, then you see that you are slowly zooming to the flat space-time. This is what you are heading to. Okay, now here your t is ranging from -infinity to +infinity, your r is heading from 0 to infinity, and your angular coordinates remain the same.
What exactly are you zooming into? I mean, what
I mean, descaling the scaling of the coordinates tau to t and r to rho. What it does, it takes me to the center of the AdS. So here it is around tau equal to 0 and rho equal to 0 that you can think of. That is where we are, and in that part, close to that part, the space-time just looks like flat.
Okay.
Okay. good. So then what have we really obtained? So our classical result that we have just obtained is, when we can think of that, we have only been able to see the signature of a very, very small AdS potential around the flat space-time patch. Okay, as Sandeep was saying a few minutes back, like exactly that's what I have been able to. So of course the question comes, is it promising? I mean, should we be, okay, I got a result, it has nice universal structure, all good, but is it worth studying it more? Now here I would like to think of following points. First is, please recall that second issue, or maybe the first issue to my goal was the following, that defining scattering states in full AdS was an issue, right? Because we cannot do that. There is no null. So I don't know how to do it. But if I can be somehow, if there is a way within AdS to think of a calculation which is valid around the flat space-time patch, then around that patch, maybe we would be able to define scattering states. Okay, and if I can do that, then maybe we will be able to find the 1/L² corrected soft factor, and that would be equivalent to a large gauge word identity around this flat patch. Okay, and maybe in the broader context, we would be really able to identify the observable in this quantum theory that will have some universal behavior. So yes, although my result is only valid around the flat patch, the classical result is only valid around the flat patch, but it gives me a hope that since it is valid around the flat patch, maybe I would be able to define a full scattering amplitude around that, and then study the effect of the large gauge word identity in terms of the soft factorization of that scattering amplitude. And then hopefully, luckily, even if I can do things properly, and if the entire construction can be done, then I would probably be able to get back my classical result in the classical limit. So that's what I'm going to do next. Okay, so let's see how it can be done. Any question?
Just to understand.
Yes.
And the reason you cannot define scattering, one way of saying the reason you cannot define scattering in AdS is that the particles cannot separate infinitely.
Absolutely.
So they never stop interacting.
Right.
Now you are restricting to an even smaller ball than AdS.
Right.
So, I mean, if your AdS radius was finite,
yes,
then you could have an even larger problem in defining scattering in your smaller ball.
Right. I mean, I don't even know how to define it, because I mean, for defining scattering states, they should be asymptotically free, right? But in full AdS, they will always keep on interacting. So I do not know how to define the in state and out state properly when I am working in full AdS.
Exactly. So if your goal was to find an S matrix associated with finite LADS, that just seems impossible, right?
Absolutely, yes.
So can you state again what your goal is? To find an S matrix associated with what?
No. Okay, so my goal is following. You were probably not there. Just let me go back and show you my goal. Yeah. So the goal is to look for physical observable in a theory in asymptotically AdS space-time. Okay, some observable. It need not be. I'm not saying that I'm aiming for finding scattering amplitude in AdS, because I know that I cannot define it. The usual scattering matrix cannot be defined. I know that the soft theorem, whatever it is for asymptotically flat spacetimes, are statements of scattering matrices. That particular aspect does not go to AdS. So my goal is to look for some observable in AdS and then try to find their universal behavior in a soft limit. Okay, that's what is my goal. So, okay, now what I have reached to is following, right? We have reached to this point that, wait a minute, just a second. Yeah. So I have reached to this point that, okay, there are certain quantities that sees the effect of AdS, a very, very small AdS potential. Okay, Siraj, just give me 1 minute. I just have to take the call. 1 minute. Sir, I'm giving a talk at 5. Can I call you back a little later, please? Okay. Thank you, sir. Thank you. I'm sorry. It was a call from the director I had to take. I'm extremely sorry. Okay. So, I'm sorry. Okay. So what I have to do now, okay. So what I'm seeing now is that a quantity can be defined around this flat patch where that shows a universal behavior. This is what the classical result has given. Okay. So now what I'm trying to do is I'm trying to define some physical observable now around this flat patch. Okay. And since I am around the flat patch, I can as well think of this physical observable of the full AdS theory as scattering amplitude around this flat.
And what do you mean by around this flat? I mean, is your theory defined by some boundary conditions you're putting at R?
Okay. What I mean is, so I have a let us just consider AdS with finite radius. Okay, I'm not taking any L going to infinity limit. Fine.
Right.
So in that AdS, I want to look for an observable that in the large L limit would behave as the creation and annihilation operators around this patch. That's what I'm trying to do.
So this AdS with finite radius is defined by some boundary conditions of those finite radius.
Absolutely. Yes, yes.
I thank you.
Yeah.
Now, Nabamita, the one question which probably you addressed already. One way to kind of just to study that patch is to have it probed by states with very high energy, so that they just see that region and not the full AdS, right?
Yes.
But at the same time, you also want to study the soft limit of such.
Right.
So how is it that the omega is very, very large compared to 1 over L is compatible with omega small with respect to what?
No. Just give me a minute. I'm going to tell you how to define this quantity around the flat patch. Okay, just give me a minute. I'm going there. No, but what?
Yeah, go ahead.
Yeah. Okay. So
I have a question.
Yes.
Like you're trying to get the AdS dual or the bulk dual of the soft theorem in 4D, right? That is the goal, right? I mean, whatever corresponds to the soft amplitude, soft theorems in 4D, you're trying to get the bulk dual of that, right?
No. Well, no. I mean, you can state it in that way. But what I am really trying to understand is there a quantity in asymptotically AdS theory that under a soft limit will show a universal characteristic? Okay, that
for under a soft limit in the boundary theory, right?
The soft limit that I have defined. My soft limit is following, that as the AdS radius is going to large, the frequency of the radiation is going to please understand, radiations now are only meaningful within the flat patch, right? Because otherwise, in full AdS, I cannot even study the scattering process properly.
Exactly, that is
because
the full AdS you can't study scattering. So
exactly, because of the what do you call it? The boundary condition. It will always come back, right?
Yeah.
So that entire classical radiation calculation itself is valid within that flat. Okay. Now what I am now trying to understand is to find a quantity, whatever it is. We will see how to get to that. Okay, that will have such a behavior in my defined limit. And that is what I am calling quote unquote soft limit for me. Then the limit is following that the radius of the AdS is going to large and the frequency of the radiation is going to small, such that their product is a large but finite one.
But could you go back to
that
slide where you showed your goal? I mean, can you, in that red line that you had?
Sure. Yes.
To look for physical observables in theories and to study their universal behavior in the soft limit. I see. Okay. It's not dual.
Quote unquote soft. Yeah.
But yeah, I mean, the thing is that scattering amplitudes themselves are not defined in AdS. So that's what I'm confused about.
I am never trying to say that the physical observable is the scattering amplitude in AdS. That statement would not make sense. Okay, so I am trying to define what is that physical observable. That is what I am trying to do.
No, my question is, what do you mean by soft limit? Because the soft limit is defined in terms of scattering amplitudes, right? So
no,
that is the
scattering amplitude. Soft limit means the momentum of the all four components of the momentum of a particle is going to 0. And we can only do it for massless particles, of course.
Yeah. So
Okay. And more to it, that's what I called a strict soft limit or a usual soft limit. My soft limit is a limit where this is true only the limit of L going to infinity. So it's a double scaling limit for me. Okay.
okay.
See, that is what I tried to say, right? There were two issues to my goal. As you can see, I have written here. First issue is I don't know what is a scattering matrix in AdS. Second issue is I don't know what is a soft limit in AdS. So far, by doing my classical analysis, I have been able to identify what I call a soft limit. Okay? Then my second point comes that what is the observable, and that is where I am trying to get. Okay.
Okay.
Can I go ahead?
Yeah.
Okay. Thank you. Okay. So again, before I do that, some facts. Okay, I know all of you know this, so I'll just like flash the two slides. So we know that we can think of these are statements for asymptotically flat space. So we know that the soft photon theorem can be thought of as large gauge word identities on the at the boundary of this space. So this is like just Strominger results, and that's the this is the result, right? So this statement is equivalent to soft theorem, and what we really need to so this part actually gives us the soft factor, and what I really need to get to this is to identify the soft modes of my excitations. Okay, so basically now what I would try to do is following, that my prime job is going to be to find these soft modes around the flat patch in the asymptotically AdS space. Okay, so if I can do that, then I can rewrite my relations hopefully in terms of those soft modes and can try to see if that resembles the classical soft factor in the classical soft limit. By that I mean in the defined soft limit that as the double scale. So our then first step is to understand that how to write down these soft modes deep inside this space. Shiraz, is this okay? Shiraz, do you have a question?
You tell us about your boundary conditions.
Okay. Say again.
I just right at the beginning of classical calculation, when you did that, were you imposing the Dirichlet type boundary conditions at radius r? Was that important or not?
So my conditions were that in that space time, if I go really extend to the full AdS, then it should be the reflecting boundary conditions. I was doing the calculation within the box, and within the box also that should be true. At that order.
Sorry, when you did the calculation within the box, did you use some Green's function for the photon? Did that Green's function obey the condition vanish at your boundary of your box?
To the yes.
Yeah, so it was Dirichlet types. Yeah, fine. Okay, thank you. Yeah.
Yes.
Okay, I thought these are just the particles, right?
Okay. So now, okay. So now, should I go?
Yeah, please.
Can I ask the question? Hello?
Should I? Sorry, I am not being able to. Yes.
Yes, yeah. So I was in your classical calculation, you had the necessity of I thought you needed the black hole, right? And then now when you're trying to do the quantum computation, shouldn't you worry about the presence of horizon when you look at the soft modes?
No. Right now, see, I have no. That is not required anymore because I'll show you. See, the result that I have derived there, I required a black hole for that, but I saw that the result is finally an universal result, right? So it really does not matter what has gone into creating that.
I see. Okay.
All that was really important is that that entire procedure could be done because we were really around the flat patch. Now in the quantum calculation, that fact I am trying to explore. Okay, I'm trying to understand that. Since I am around the flat patch, now around the flat patch, can I do something more? Can I write down the modes now? Because being around the flat patch, that gives me this boost, right? That, I mean, by boost, I mean that gives me this possibility of being able to define those kind of modes. So that's what I'm trying to do. So now my goal. So now my goal is to find these soft modes deep inside the AdS. And as it turns out that this problem was studied by Hijano et al. In this paper. In this paper, it's a very, very, I mean, I really find the paper very useful, detailed and clean. Okay, so what goes into the construction? What goes into the construction is following. I have just tried to point out the main things. So first, we can use HKLL prescription for constructing the bulk operators that produce the CFT correlator. I mean, and it is just equal to the bulk correlation function as in accordance to the AdS CFT conjecture. Okay, so given a boundary condition, I know what should be my boundary operator. That's my boundary condition for every bulk field. With that boundary condition, now I'm trying to construct an operator in the CFT whose CFT correlation function is exactly equal to the correlation function in the bulk at any R, at any radial point in the bulk, as the AdS CFT conjecture should tell us. So that's what is the first step of this prescription. So with an operator in the boundary, construct the corresponding operator, which is now R dependent, such that I can write down the correlation function not only in the R goes to infinity limit, but for any finite. Is this statement clear? So this is, I mean, this is what the HKLL does for us. Okay? So my first statement is first do HKLL, get the operator in the bulk. Now, so now I have a quantity defined in the bulk at any point. Next step is now we take the L going to infinity limits of the circuit. What it will do is it will just bring me to the flat patch. It will bring the operator to the flat patch. So now I have an operator in the flat patch whose correlation function that you can also make as an S matrix would be related to a CFT correlator that you have found in the CFT, in the boundary CFT, boundary of your full AdS. That's it. Okay. Step 3. From these operators that you got around the flat patch, you find out the creation and the annihilation mode for the normalization. Creation and annihilation operators for the normalization. Now, with this operator, you define the S matrix. Then you map the conformal word identity statement in terms of these quantities. I mean, in terms of the quantities that we have defined, that we have obtained around the flat patch, the conformal word identity now will start looking like the large gauge word identity. And from that, you try to understand what is the soft patch. Okay? That's the whole, I mean, that's the whole program. Was it okay, or should I repeat?
I was going to ask you if the soft theorem that you would get would map to the conformal word identities of the boundary. So wouldn't there be an independent way to study some scattering process and do the soft limit and see that it matches with the CFT word identities rather than starting from it? Because you have to somehow encode the local bulk physics also into it, right?
See, but the statement that the large gauge word identity will be mapped to the CFT word identity would only be true in this limit, in the larger limit, right? So all my statements, so my physical observable that I was looking for is finally these operators and their correlation functions in the larger limit in AdS only. But it's not like independent of this limit I can construct it. Yes, Sandeep.
No, but I have a question about that, about the relation between the conformal word identities and your word identities, which is, it's not clear to me that yours are related to the conformal. Maybe I'm missing something, but the reason I'm saying is the following. The conformal word identities are related to asymptotic isometries in AdS space. And here, by looking at a box, I mean, you're looking at different kinds of gauge transformations or coordinate transformations, isn't it? Or maybe I'm missing something.
So let me tell you what. I'm just give me a minute.
I must be missing something, but
I
just
think blue is good. Okay, no. Just give me a minute. Let me go back to this picture. Okay. So this is my AdS. Okay.
Mhm.
In the boundary here, I have CFT. Okay. So I have certain operators here. So yeah, let me denote the CFT coordinates by let me write tau and omega. Okay, that's my CFT coordinates at rho equal to pi by 2. Now with this CFT operators, with their help, I am going to construct certain operator in the bar. So my operator is going to be some phi which is defined as tau, rho, and omega, such that appropriately in the boundary going to map to tau and omega. Okay.
Right.
Now I know that for all these boundary operators, when I have inserted the correct source function, for this case the charge current, and write down the corresponding word identity, it will satisfy the word identity. That's a statement of the CFT. Okay, that's my conformal word identity.
Yeah,
now, what I'm trying to do is, now from these operators, I am constructing this bulk operator. Now this. After doing this, I am taking, so this bulk operator is defined at any tau, rho, and omega, right? Now I am taking a large L limit of it, L going to infinity limit of it, such that I'm doing this as well as I'm going to T, R, and omega coordinates defined by this relation. Okay? Then by doing this, what I'm getting is, in this limit, now my operators are going to sit here.
Yes, I agree.
Okay. And the conformal word identity that I wrote would now, I mean, just following this process will give me a relation between these phi s.
But
involving these bulk operators, right? I will show you the equation also. I'm just trying to give it to you first pictorial.
Yeah, I see. But
now
I mean,
after
it will give some relation, but is it what you seek? Because I mean, for example, anyway, you should go ahead. But in asymptotically flat space, you have a very large class of soft theorems, right, corresponding to all gauge transformations which meet certain conditions. No, if I'm right. And conformal symmetries are a finite dimensional group, right? Okay, go ahead. I know little about the subject. Please go ahead. I'll wait till the end. Yeah.
I have a basic question. I mean, this patch that you are considering is at the center of the AdS space, right? That's what you're saying, right?
Yeah, in this limit, I am reaching to there.
So
yes.
what is the value of R for it?
No, in this patch, R is ranging from 0 to infinity. R is the coordinate inside this patch. R is the radial coordinate in this patch. My global radial coordinate is rho, which is ranging from 0 to pi by 2. This is the map between R and rho.
No, okay. So in that metric, maybe it's something else. But when you write it in terms of that 1 plus phi plus L square by R square type of thing, or was it R square L square?
That was done in isotropic coordinate system. So there are multiple coordinate systems that are.
Yeah, but in that coordinate system, also it would correspond to something which, when you take
so that R would be related to the modular. Okay. So you go in this region, you write first the black hole solution, then that black hole.
Yeah, black hole solution.
Then that black hole solution you write in the isotropic coordinate patch. There the is equal to R.
Yeah, I'm just concerned about the fact that if you take the center of the space, wouldn't that also mean that you're taking the R going to 0 limit in that?
No, I'm not taking R going to 0. Not at all. This Sky plus or Sky minus are larger at R going to infinity.
I see. Nabamita, you have to go on, but just as a final statement of fact, so then the following is true, is it? That large gauge transformations vis-a-vis the box, ultimately when embedded in AdS, will all be asymptotic isometries of AdS. Is that the statement?
Okay. Yes, that's what we are.
Fine. Okay, at least I understand the statement. Okay, thank you.
Okay. Okay, no, thank you for questions. Okay, good. So that's what I'm trying to do. And how much time do I have? I have time. Okay, good. So let us, so if the prescription is clear, what we are trying to do, let us just quickly see how it would go for you want it. Okay? I mean, it would be clear also. That's why I'm writing it down. So first of all, our first step is to understand the normalizable AdS bulk solutions associated with this particular boundary condition. Okay, so my boundary condition is for the normalizable modes of my gauge. So mu, now we can find mu by the HKL prescription. So these J mu's, just a minute. These J mu's are my boundary currents. So given a J mu, given a boundary current, I can construct the bulk operator via the HKLL prescription with the HKLL kernels. These are all for scalars and vectors, these are known. And also, of course, for other spin fields, one can construct it. The construction is very well defined for any spin. So this K, this kernels, like any other Green's function, actually a kind of a Green's function only, it has two arguments. One is capital X, which is the bulk argument and bulk of AdS, and X prime, which is the boundary of AdS. Okay, so the prescription is you take this kernel, multiply it appropriately with the source operator, and then integrate it over the boundary directions, that's tau and sigma for me, and then it gives me the operator in the bulk. That's the first step, right? Where I wanted to construct a bulk operator which is equivalent, which is sourced by a corresponding boundary. So I have done that. And then the next step is I want to take the large L limit of this. So at this step, if I take the large L limit properly and go from tau, sigma, and omega to T, R, and omega, that I'm calling, this set I'm calling Y, I'll get this operators around the flat patch. Okay, so now I have the operator around the flat patch. All I'm trying to do is, around the flat patch, I'm going to define the creation and annihilation mode. So I just take the Fourier transform in that space with appropriate momenta. That momenta is what I'm calling here Q. And if I want to find the outgoing, for the outgoing modes, I'll take the T, this T, that's the T in the flat patch. To plus infinity limit, if I want to get the incoming mode, I'll take it to be minus infinity. So I have been able to define a way to construct in state and out state in my theory. When I say in my theory, I mean around that patch. Okay, please understand the input for this entire construction is this current. The current is at the boundary. With that knowledge, I have been able to construct the creation and annihilation modes for my in state and out states for a theory around my flat patch. Any question?
Nabamita, these in states and out states are at what? I mean, do they have momenta much smaller than your R? Localized on length scales much smaller than your R?
Yes, it should. Yes.
Okay. And in that parameter, localization length divided by R, they are effectively non-interacting. Is that right?
Exactly. They are effectively non-interacting. Exactly. Because I have, yeah.
Yeah. So it's as Abhijit was saying earlier, basically you're taking a high energy. Your modes are very small compared to your.
Right.
Thank you.
I mean, what I'm trying to, what we will see that for such objects, like the soft limit that I have defined is making some sense. Okay. But on the same, similarly, this is also true that I can reach to these objects starting from a quantity of my full theory, of the full AdS, right? Because these J's are just the CFT currents.
Yes.
Okay. So this is fine. And then the last step in this process would be to understand that we would be interested in modes which are giving me soft modes. So I have to take the zero frequency limit of this modes. So that's the last. Okay. And just to tell you like where this whole thing maps. These guys are really the boundaries of my AdS, and this I have this diamond here in the center. So when you do this calculation, you can explicitly check that for the massless particles, the major contributions comes from these two slices, the tau equal to pi by 2 for outgoing modes, and from tau equal to minus pi by 2 of the boundary for the incoming modes. Those, they are actually giving me the contributions, the major part of the contributions, the leading part of the contributions for my modes, soft modes defined in this patch. And actually one can nicely show how this whole thing, how both the asymptotic, one is the asymptotic around the flat patch, and I mean the flat asymptotic, and another one is the real AdS asymptotic. How these two things match can be explicitly shown. Yes, there is a question. Yes, Shanti.
It's just ratio. So just Nabamita, here, in order to get to the patch, you increase the energy of all the modes. But now you also want to take the soft limit. So that means that the energies of one guy is much smaller compared to the energy of the other guys, right?
Right. Like no. Say again, please. Say again.
No, I mean, in order to get to this small patch, I would imagine that you increase the energies of all the modes that are involved in the scattering process. You took it to be much greater than the AdS energy, and then in order to now define the soft limit for one of these particles, you would take its energy. While keeping its energy big, you would take the ratio of the energy of this guy with the rest of the guys to be very small.
Right. Okay. I will finally do it in 1 over gamma. Yeah. Okay.
Yeah. Yes. Thank you.
Yeah. So. Okay, this is just, I mean, this is what Sandeep was asking me. I have just written down the statement of the conformal word identity. This is the statement of conformal word.
Right.
This is the usual statement. What I'm trying to do, I mean, yes, I am just writing an integral version of it. What I will show you is that this equation will actually now, see, what have I done? What I have done is, given this J mu's, I have understood how to write down the operators in the bulk. So I'm going to write this left hand side here in terms of the bulk operators, and then I'm going to interpret the right hand side in terms of the soft part. That's it. So the word identity is what it is really doing for me is for this these X operators, bunch of operators in the boundary. If I insert the source current and then take this relation, it tells me how this correlation function is related to the correlation function without the source current. Right? All I'm going to do is I'm trying to map this relation such that this source current will now somehow give me, not somehow, I mean by the prescription I told you, will give me the soft modes in around the flat space time, and this entire relation will come out as the large case word identities.
Okay, I see.
So basically.
Yes. Sorry, you should go on.
No.
So geometrically, what you're saying is, because these are asymptotic isometries in AdS, is that the large gauge transformations correspond to how you embed the box in AdS, right?
Right.
Okay, I see.
Right.
And just to say, I'm very, very sorry, because I know you're going to have much more to say, but since we have exactly the same, word identities in de Sitter space, because again they just arise from large gauge transformations which preserve the asymptotic isometries of de Sitter, you can probably just generalize this there as well, right? All you you don't need HK. What I'm trying to say is you actually only need the statement of word identities at the level of correlation functions, right? You don't need a detailed ADSC.
Right.
Okay. Anyway.
Right. In fact, I mean, so far my classical calculation was like, all I did is I was studying lambda as a small perturbation, right? Now I take that plus or minus in that calculation, it shouldn't have mattered much.
Yeah, it shouldn't matter, right. But I'm also saying just from the relation, everything you do is geometric and works equally well, it seems to me, in DS, right? Because again, you embed the box in different ways in DS, and you have, again, very similar statements coming from the asymptotic isometries of DS, which result in relations. Okay.
Yeah, I think that's okay. Okay. So
just a
okay,
small
yes.
question.
Yes.
Since you're just taking the HKLL construction of the current, but what about the why aren't you taking the HKLL counterparts of the other operators?
I am only interested in understanding soft photon theorem. Okay.
Yeah.
So my boundary condition I gave you. Just give me a minute. This is my boundary condition. The first line. Okay. So yes, Shonda, actually what you asked is a very nice. I mean, it is a useful question. One can do it for other kind of operators also. So of course for scalars it has been done, but since my interest is in understanding the soft photon theorem, I am interested in understanding it with a current operator in the boundary. If somebody wants to do it for gravitational, one can also try to do it with stress tensor. I have not done it yet. Yeah.
Usually, the soft theorem is usually connected to the correlator to the scattering in the boundary, right? I mean, scattering amplitude.
That is a hard particle. Shomda, that is for hard particles, right? So yes, let me go back to this. So that information is here. Yes. So these are my hard particles, like which are being created by such operators like those that I'm talking about in the CFT.
Yeah.
Yeah. What I am trying to understand here particularly is the soft mode. What the soft mode along with these hard particles. I mean, in other words, if I can think of this CFT word identity, where these X's are going to play the role of the hard particles, and this J mu is somehow will give me the soft insertion in the plan. Okay, that's what I'm trying to.
Yeah,
one suggestion to the audience, given that the speaker has a hard stop at 12 o'clock, perhaps we can keep our questions till the end and let the speaker finish.
Okay.
Okay, thank you. So where was I? Yeah, here. So basically, as I said, so recovering the flat space-time result from CFT word identity. As Shondeep was saying, like, we can picture.
Yeah.
So we have lost her again.
Yes. So she had asked someone to give her a call.
Yeah, Tabassum, are you Tabassum or Arpita?
Yeah, I am not at the campus. Okay.
Oh, sorry. I'll also try to call her.
Hello. I have informed ma'am. Okay.
Yeah, I'm trying to get again connected.
Thanks. Okay.
Sally, can you disconnect me from there? I'm not even being able to leave the meeting.
Okay.
Hello?
Yes, I'll do that.
Yeah, I'll share again. Is my screen visible?
So now it's not visible yet.
Is it visible?
No. So you have joined only from one device. Maybe you have to join from the other device.
No, I don't think so. I have joined from the right device, but just give me a minute. I hope I can share, right? I didn't share. Just a second. Is it visible?
Yes, yes.
Okay, just give me like 1 more minute. I'm sorry. Okay. Okay, you have removed me from the other account, Shaili, so I cannot join, but that's okay. So if Shurajit or Tabassum, anyone from Bhopal, please call me if I am again out, okay? Because I wouldn't know. Okay, good. So this is where we are. And now let us just, as I said, let us take the limits and see how we could get to it. So first of all, one can show that one can identify the outgoing creation mode as this factor with the boundary insertion JZ. And then the conformal word identity, when one writes it down in terms of these quantities, in terms of these modes, then it just reads like follows. To get to this, we also need to identify the Gauge transformation parameters to this quantity. This is the usual identification of the Gauge transformation parameter as is done by Strominger. So if you do that, if you take the same Gauge transformation parameter, you can see that the conformal word identity is now just giving you this relation. This is exactly same as in the same form as the large gauge word identity, where in the left hand side I have a soft insertion with other hard insertions, and in the right hand side this quantity in the frequency expansion is related to amplitude involving only the hard particles along with this factor which is related to the soft factor. Okay, so we get that. Okay, I'm connected, right?
Yeah.
Okay, I'm sorry. Okay, thanks. So this gives us the soft photon theorem with the correct gauge parameter and the soft number mode in accordance to the large gauge identity, large gauge word identity. Good. So this is what these people have done. Okay, Hijano and Neuenfeld in their 2005 paper, but of course their analysis is strictly in the L going to infinity limit. So they just recovered the so-called leading in L factor of the soft mode. Now what we are interested in is a step ahead of it, right? We have found the effect of the small cosmological constant to the classical soft factor, and we would like to see that part of the large gauge word identity by doing a similar analysis. Okay, so basically what we would like to do is we will try to find the 1 over L square connected soft theorem, but from the conformal word identity as I told you just a few minutes back. So the procedure remains the same, but now we need to write things keeping the first order correction to every possible terms, whichever one are important, and then see if we can get back the classical soft factor that we had in the classical. So that is what we have done in the recent paper. And few points before I tell you the results are important. That first point is that the flat patch does not change to this. I mean, if we keep the 1 over L square correction, one still gets to the flat patch on. Okay, so thus even after taking the 1 over L square correction, we will actually be looking at scattering processes around the flat patch. This is what we have understood earlier also, that why that is true. The modes that we are interested in will not take me out of this patch. Those kind of modes are what would be important in this limit. And then the hard insertions and the boundary currents are also going to be same. because those are statement of the boundary and that's not going to be affected by this. So that all the formal expressions of the mode operators will remain same. But what will change here, I mean, where we need to take the effects into the limits property are the HKLL operators, because that depend on how you move from the boundary. That detects when you move from the boundary to the bulk. Those operators, the HKLL operators, does that job for you. So there one needs to take the 1/L² correction properly and take the limits properly. So that is what we have done. And when you do that, then you see that other than the mode, the soft mode that I wrote here, to the order 1/L², we get these corrections. Okay. Where the gauge transformation parameter, the correction to the gauge transformation parameter as well, can now be identified as this integral. Okay, where this omega is basically any. So I have this flat patch and then I have the pi/2 boundary of AdS. So any angle in between. Okay, one has to integrate it over. And that's the modified correction. I mean, that's the correction to my soft mode excitations because of the AdS, small AdS potential is what we get. Okay, question.
Just a small question. Your scattering is taking place inside the bulk, right? I mean, inside that patch that you defined, right?
Right.
And but your boundary, the OX operators, they're all in the boundary, right?
So scalar will be not
correct. The OX operators are all in the boundary. So how can the scatter with things in the bulk, unless you take the corresponding?
That is what the
counterparts of the.
Right?
Huh?
Shomda, that is what the HKLL did for me. With those boundary insertions, I have constructed the bulk operators, right? I mean, you can call it the bulk operator and you can call it.
You constructed the bulk operator only for the current and you left the OXs alone, right?
Right, the are still there.
Yeah, but unless that there is an effect of the OXs in the bulk where the scattering is occurring, how will the JMU scatter with things in the bulk?
No. I mean, this is how you are. I mean, this is, see, I can look at this entire result just from the conformal word identity, right? Right. So in the conformal word identity, I suppose you have no question. That's a statement in the CFT itself. Now all I am doing is I am taking all the operators and pushing them by doing HKLL to the bulk, and then taking the large L limit, so that now all of them have come to the flat patch. But it is the same statement, right? The statement remains the same. I am just then doing the HKLL construction on it for every operator and hence on the entire relation.
Yeah, if you do it for all the operators, it's okay. But if you do it just for the JMU, then it's not. That's what I'm saying.
No. Oh, sorry. So here I'm trying to tell you how to identify the soft mode. Okay. So the soft mode is just related to JMU. Okay, because the soft mode is related. So because I have, I mean, what is J? J is the boundary condition that I have given to my A field, right? And that is what, when is being mapped to the flat patch, is giving me the creation operator for my photon, soft photon. Yeah. I mean, in particular, creation operator for photon, and then once I take soft limit, it's the creation operator for the soft photon.
True.
Okay. True. Okay. Good. Okay, so that's it. And then the last step remains where I have to take the classical limit of it. So again, some details goes into it. So what we need to keep in mind, that this is the question that Shomda, you are asking me, right? That these other hard operators were at the AdS boundary, but when I have pushed them back, so they have all now come to around the flat patch. So all these Z primes, the angular positions of the hard particles have also now, their directions are now towards the flat patch. So you take the smallest regulated scale of your theory as epsilon, where the ZQ and Z, these Z's are for external particles, all the hard particles, they are small. And you also consider that all, I mean, basically now you do not have a difference. I mean, it's a very, very small length scale that is involved here. So in that length scale, the Z omegas can also be expanded in terms of either of the boundaries. And once you do that, I mean, this is how I'm defining my limit, classical limit. Once you do that, you recover exactly the right gauge transformation parameter that appeared in the classical version of the soft theorem. Okay, this is what the CFT conformal word identity gives me. Okay, and then this is exactly the result that we had earlier. Okay, so we can, of course, up to order of 1 over gamma square. So what I'm trying to say is following, that the SLEM is the perturbative correction to the S flat EM, where S is nothing but the soft factor, and that matches with the classical soft factor that we had obtained earlier. Okay, so following extending the Hijano analysis to take into account the effect of the small cosmological constant in the soft limit that we have defined, we find that we can rewrite, we can get the effect in terms of the conformal word identity, or we can similarly interpret it as the corrected large gauge word identity in presence of this small cosmological constant. That's the result. Any question? Am I connected?
Yes.
That is a question from my side. Okay, so that's the result. Let me summarize, and then if you have questions, I'll be very happy to take. So these are points that we have obtained. Okay, so we have studied the classical scattering of a probe particle in an AdS black hole background. We worked in the small cosmological constant limit and considered AdS potential as a perturbation around the flat space. Okay, so I must say that, yeah, in fact, this is exactly what we did. The third point is, then we defined a quote-unquote soft limit as this following limit, that the frequency of radiation is going to 0 as the AdS potential is becoming smaller and smaller, which means the AdS radius is going to large values, keeping their product finite but large. Then we found the classical soft theorem for such a theory and extracted out the universal soft factor from it. Next, our analysis provides us this small lambda correction to the known results of electromagnetic radiation. Actually, we have also done it for gravitational radiation around the asymptotically flat space-time patch. Finally, we constructed a soft photon mode in the flat patch at the center of the asymptotically AdS space and computed this quantum scattering in their presence. And we saw that the soft scattering gave us the soft expansion, and it reduced to the classical results in the classical limit. Okay? So the physical observable that we were interested in identifying in the AdS is following, that fixing for a fixed boundary condition, one needs to get the corresponding bulk operator in the larger limit and then look at scattering processes involving those objects. That when one takes the quote-unquote soft limit of that scattering amplitude, one gets a universal factor out of it times an amplitude without the soft insertion. So this is what we have been able to establish in a theory where the cosmological constant is small. Okay, so how far we are from our real goal, right? So what we have defined is, we have defined a consistent notion of soft limit in these theories. That is one point that we think we have been able to get. Second is, we have identified the observables, as I said, the bulk correlators that in the flat limit reduces to the scattering elements in the flat space-time patch at the center of the AdS, and they show the universal soft structure. So in particular, we get the corrected soft photon factor. Our analysis is only for spin 1 right now. And these are perturbative corrections to the flat space-time results in such theories. Now, the next step, what remains to be done is, if our this process is correct or is meaningful, then we should also be able to do the same thing for soft graviton. That will give us more confidence on our prescription. Then the question remains is that how does this soft limit behave in the context of, for example, say the way Abhijit is looking at the the scattering amplitudes within AdS, right? He has his way of defining scattering, some correlation functions in the AdS that under the limit that he is considering really reduces to the flat space-time scattering amplitude. So in that context, if we study the small frequency limit as well, what would it mean for the bulk, for the AdS quantities that he is defining? So that would be nice to look at. We are actually looking into it. And then the question that I think would really be nice, but I do not know how to really get to it, is following, is this. That is, can we just write down a scattering amplitude in the CFT? When I say scattering amplitude, I really mean not in terms of not a CFT correlator, but really looking at the particle states in the CFT and then writing down a field theory, the usual field theory scattering amplitude in CFT. Okay, and then so if I can do that, and then I take those observables in the bulk and then take the soft limit in them. Now when I here by soft limit, I mean the soft limit in the field theory in CFT itself. Okay, so this does not require me to take L going to infinity. I'm just talking about do usual AdS CFT, write down maybe some of you already know how to do this. It's just that I do not know. So in the CFT, I write down the scattering amplitude. Okay. And I know that that should definitely have the usual soft limit. And then rewrite this entire statement using the AdS CFT dictionary in the bulk. Now, not necessarily in the large L. So that will tell me the interpretation of the soft factorizations of the field theory in terms of bulk quantity. Okay. After that, this should be the step one. After that, one can try to see that if our way of taking soft limit is important or manifest in this process or not. But this is what, in principle, you asked me like, what is my goal? My goal would be following. This is what I would really like to do, not without taking the large L, but to really see that the soft factor, the soft factorization of a field theory amplitude in the context of AdS CFT, how it gets mapped to a relation in it. But yeah, as I said, so far I have not been able to do this. Okay, and then probably I would like to understand that the limit that we are talking about, if that comes out of this analysis, okay, which a priori should not depend on any limit on the radius of the AdS. So yeah, that is what I would like to reach to, and these are some of the references for the talk. Primarily, the paper by Hijano is very, very nice. This one. For the quantum part of the analysis, it's nice. And for the classical part of the analysis, I forgot to write Sen's review, Sen's papers. Those are very, very good. And for bulk reconstruction, of course, there are many, many papers, but this one by Nirmalo is nice. Yeah. So thank you. That's all from my side.
Thank you, Nabamita, for such a nice talk. There were already lots of questions. So Somidatta has a question. It's in.
Yeah, so your main goal is to calculate the SLEM, right?
Yeah, my main goal is to calculate SLEM. Let me see what you mean.
The soft photon correction when you have a finite L.
Right. Right. You are asking me from this. Yes. My main goal is to understand that for a finite L, what would be the interpretation of the CFT soft theorem in the bulk? Yes.
No, but this soft photon factor, that comes from scattering amplitudes, right?
CFT is a field theory, no? So it's I have no problem in defining scattering amplitude.
No, wait. what I'm saying is this: when you're saying that you're considering the SL, the soft photon correction to the flat space limit, what you're essentially saying that you're considering the amplitude in the AdS space, right? When you have
So Shomda, sorry, let me understand your question. Is your question is from the last point of my presentation, or is your question is from?
No. I mean, what I'm saying is, in what sense does it make sense to say that you have a soft photon correction to the flat space limit when the correction itself is in the AdS space? Because in the AdS space it doesn't exist. In the AdS space there is no scattering.
No. See, what is my theory? Let me show you. Just a minute. I hope I'll go back to the right slide. No. This is my theory, no?
True. Yeah.
So I think that's answered your question.
See, in AdS space, there is no such thing as scattering.
Of course.
That's
the whole point. Yes.
Yeah. So, what sense does it make sense to say that?
But Shomda, 1 minute. Shomda, yes, in AdS space, we don't know what is in full AdS theory. We do not know what is scattering matrix. But what I tried to explain in today's talk is, in the same space, if I go to certain region, which is very mathematically well defined how to do that, you do have a notion of scattering, right? That is what I tried to explain in today's talk.
What is that?
Okay, and that's exactly the flat patch at the center of it is. And you know how to mathematically go to that. I mean, your full theory is the one that I have written. Now, I am telling you that how from the information of this full theory, I can really get I can get information around the flat patch where the same information can be interpreted as a scattering amplitude. Okay. Scattering amplitude of that theory, defined there. It's just a correlation function. So far, the whole theory is considered a limit of a correlation function, you can say. Okay. So that is what see, this way of doing it, things works. That's what is our analysis telling me. But that's not what I really want to do. Okay. I really want to understand that without taking this L going to, I don't want to begin with L going to infinity limit. Let me put it in the proper way. I want to see that when I would be studying the soft theorem in the CFT, would I be somehow forced to take this limit? Which to begin with does not look like, right? Because AdS CFT is valid for any L. All I'm trying to understand is a statement of CFT's interpretation in AdS. Right? So I should not be, I don't see that why it would force me to take L going to infinity. That is what I would like to see. Okay.
Yeah, and I suppose since scattering amplitudes are finally related to the correlation functions, just the HKLL construction will tell you how to do that in AdS space.
No. HKLL construction just tells me, well, I do not know how to, I have not yet been able to do that. Maybe, yeah. So far, HKLL constructions definitely tells me how to do that around the flat patch. Yes, it does. Because until unless I'm reaching to the flat patch, I cannot interpret certain operators as creation and annihilation operators of in and out state, which is required to define a scattering matrix. Right? But please understand that my goal is not to be able to define scattering matrix in a space, in AdS space. Because if that is my goal, then this is what I have to do. But that's not my goal. I would like to define any physical observable. Okay, that will somehow understand. That will have an interpretation of the soft split. That's what.
Nabamita, perhaps I was wondering whether this is maybe a rewording of what you're doing, just in terms of this bullet point again. So, as you know, there's this relationship between coefficients of the multi-point singularity and flat space S matrices. So now suppose you had a correlation function with, let's say, four charge scalar fields. That would the multi-point singularity of that, the residue of the pole of the multi-point singularity there would be the flat space matrix of four charge scalars. Now you consider another correlation function, which is four charge scalars plus a JD on the boundary. Okay. Now the correlation, the residue of the multi-point singularity there would be have the interpretation as four charge scalars plus a core. Okay. Now on the boundary, as you've said from your ward identity, from your U1 ward identity, that there's a relationship between these two correlation functions. Because you del mu J mu, and that is related to just the other guys. So if you use that tells you that from this multi-point singularity, there's a relationship between these two experiments.
Okay.
And therefore, from the you could probably very simply go from the this equation to some relationship between coefficients of this multi-point singularity, at least at leading order, not your calculation, and get the soft theorem out of that. Is this a reasonable way of rewording the first part? No, I mean the part before your paper, the Hijano part. I think that some leading connections to the multi-point singularity would be your theorem. Does that sound right?
Yeah. It should be. So
keeps on giving words that higher. But the some leading connections may not be so
Abhijit can't hear.
The nature of the sorry, but I just one more question that actually Abhijit brought up, but he hasn't asked yet. But let me ask it. It's vaguely I've heard that there are some leading, apart from leading soft singularities, there's a subleading soft singularity. Is that true for the U1 theory?
Yes, there are subleading. By that you mean like their effect should be subleading soft theorems, right? Yes. Is that what you mean?
Yes.
Yes.
I mean that apart from this, the leading, this K dot Q pole, right, there are also subleading.
Yes.
Okay. Now, will those also come out of the same U1 mod identity on the boundary?
Yes, in principle, yes. But so far it has only been shown for the leading term. So what you are asking is like now the left hand side that I have, if I expand it in omega, then can I see it or not, right? Can I see the next order term in omega or not? That's what you are asking.
I suppose I was asking whether that's the source of information from the boundary correlation function is the same U1 mod identity for both soft theorems.
Yeah,
you both. Whether that's
I would think so, because I would not say that the statement is still that word identity, but now we are writing down that word identity both sides order by order in omega expansion.
Okay.
Right? So if the expansion can be done properly as it should be done.
Okay. And then, just to follow along these lines, presumably it's the conservation of the stress tensor. You were saying this. Remember?
So, no, I was saying that the classical result that we have, that not only sees the leading term, but the log omega term can also be seen in that. In the classical, yeah. So here also, what one probably it would be like, I mean, algebraically a little bit more involved, but what one has to do is to expand this quantity, both sides of it in omega appropriately.
Yeah.
Right? The leading one is going as 1 over omega. The next one has to go as log omega because we are in 4D. So okay. So what I mean, Shiraj is following that how to go from quantum soft theorem to classical soft theorem, keeping the subleading and sub-subleading order terms is something that Ashok has told us, right? But that is definitely for asymptotically flat spaces. But the same thing now we need to implement at the level of conformal word identity. The same relation, two leading orders giving me this result. when one takes the soft limit to subleading order, one would see how it is. Okay. Now, having said all these things, are you only interested in the strictly larger limit? Will you be happy with it?
I'm interested. Whatever is easy to do.
Yeah, I think strictly larger limit would be easier. Okay, because otherwise, when I am also trying to take, I'll tell you why it is even physically difficult to think in presence of small. I mean, in presence of the AdS potential is following that. If I want to keep the effect of the AdS potential, then I need to make sure that, that no back reaction effects are important. You remember that for the classical calculation, it was, although I am doing it in the AdS potential, but it was actually the classical part of the trajectory that was contributing. Okay, because we were looking at that kind of a limit. So if the omega expansion does not affect this limit, then we can do it. Otherwise, if you just forget about like the 1 over L square correction, let's say I am only interested to the leading factor. I mean, by leading, I mean leading in L, leading in cosmological constant, 0th order in cosmological constant. But I want to get this result from the CFT word identity. I think it is possible. I will look into it, and once you guys are here, we can talk about it. Yeah.
One quick follow-up question, and I know you have to go, but just very quick. At least in the case of the super translations, the super rotations, and so on, though I know very little about it, I hear people say that for some sufficiently subleading software, what the symmetry analysis in flat spaces corresponding to that is mysterious. That that they talk about how you have to turn on non-normalizable modes for that, modes that grow. I was wondering, but you've got a beautiful principle, namely just conservation of the stress tensor of your boundary field theory, and it looks like there should be nothing else. And I was wondering whether this apparent mismatch be explained by the fact that Strominger and friends only their boundary is only 2-dimensional, but your boundary is 3-dimensional. And could it be that expanding along this extra direction gives you more power?
Okay, so first of all, for that I need to see how this entire construction is going for spin 2, right? So, okay, so in that case you have super translation and super rotation. For the photon case, it's only the entire large gauge word identity. What we can see is the entire large gauge word identity. So I would hope that if I can do the similar thing for gravitons also, I mean, then probably I can answer you better, but it should in principle be possible. But on the other hand, Shiraz, this is also true that Strominger's way of doing it does not give me the log omega term. Shaili, please correct me if I'm saying it correct, right? It gives me 1 over omega and then omega to the 0 part. I mean, those two we can see from the word identity, but the log omega part, I don't think we have been able to understand it from the word identity yet. Right, Shaili?
Yes, it's even in flat space, the log omega part is not understood yet.
Yeah, that's what I'm saying. Yeah. So see, we are right now just trying to understand the flat space result only, but using AdS CFT. So that log omega part, which is the first subleading part, that can be.
Yeah, for our case, this subleading part is not universal. Like subleading photon soft factor is not universal. It depends on the background quantities.
No, that is okay, but let us just look at the universal part of it, right? I mean, there is an universal part also. We can look at that.
Sorry,
Shiraz, sorry guys. I mean, I have a class from 12 o'clock. It's already 12:05. I'm really sorry. But I have to run. Okay. Bye. Thank you. Thank you very much.
Okay. Yeah. Thanks a lot.